Elimination reaction is a type of organic reaction in which two substituents are removed from a molecule. Elimination reaction often results in the formation of a new pi bond. Elimination reaction often results in the formation of a new pi bond. Now, let me explain something here. In the case of substitution reaction is the replacement of one functional group or one atom with another. In the case of elimination, you're removing without replacing. And once you've done that, it always leads to the formation of a new double bond. Now, there are different types of elimination reaction, right? So I'll just want to talk about the types of elimination reaction, and then I'll now focus on the one we want to discuss today. I don't want to just be talking about general terms. So the first type, so we have the first one, 1-1 elimination. We have the second guy, 1-2 elimination. We have the third guy, 1-3, 1-4, 1-5, 1-6, and so on and so forth. So this is actually known as alpha elimination. And this guy is known as beta. So we're going to be focusing on this guy. Note 1-4 and 1-5. Sorry, 1-5 and 1-6 elimination always lead to cyclization. 1-5 and 1-6 elimination always lead to cyclization. That's formation of a ring in brackets. 1-5 and 1-6 always lead to cyclization in brackets, formation of ring. That's basically what it means. So formation of rings. So in the case of 1-2, there is always formation of a double bond. In the case of 1-5 and 1-6, there is formation of a what? A ring. So yeah, 1-3 can also lead to cyclization. So if I have something like this, let's say I have CH2, let's say look at this, CH2 and let's say C2OH. If I remove OH from here, from the first, let's say this carbon, and I remove H from here, that means I remove H, I remove OH. Isn't also? There will be a need to join this carbon and this carbon. So this now becomes, I can write this guy to be this CH2, this CH2, and then I'll just join them. So this has formed a ring compound, cyclopropane. So, all right, so let's put down. Please, beta elimination involves loss of two atoms or group of atoms. Yeah. Beta elimination involves loss of atoms or group of atoms from adjacent carbons. It involves loss of atoms or group of atoms from adjacent carbon. From adjacent carbon. Full stop. Now, the product of beta elimination is always formation of a new pi bond. The product of beta elimination is always formation of a new pi bond. Brackets, double bond, or triple bond where necessary. Brackets, double bond, or triple bond where necessary. So let's say we have something like this. I have this, and let's call this guy H, and let's call this guy X. Now you have this. You have a base, because the base is actually what is going to make this to happen. And all of a sudden, please remember when I said 1-2, 1-2 does not necessarily mean that the first atom that will be removed must be from carbon 1. It must not always be from carbon 1. It simply means if the first guy is coming out from carbon 1, the next one should come from carbon 2. If the next one is coming from carbon 2, the next one should come from what? Carbon 3. Adjacent carbon. Adjacent simply means carbon that are facing each other. So this guy is adjacent to this guy. Do you understand? So that one is not basically the IUPAC numbering. One to simply means if I have carbon 1 to carbon 5, if the substituents are removed from carbon 2 and carbon 3, those two carbons are adjacent because if you count 2, the next guy is what? 3. Are you following? So imagine we have this. This is a base. Remove this guy, remove this guy. Once you do that, this becomes plus HX. Now you notice that this carbon is now lacking one bond each. This is lacking one bond. This is also lacking what? Now there will be a need for it to produce what? Double bond. So that's basically where the formation of a new pi bond comes into, right? Okay, so since we've understood what E2 elimination reaction is all about, this guy has different mechanisms, just like we did yesterday for substitution. After we must have understood the concept of substitution, there are different mechanisms, SN1 and SN2, right, in which substitution can take place. So for elimination reaction, we've understood the concept of beta elimination. There are three mechanisms in which this guy can actually follow. We have the E1, we have the E2, and we have the E1CB, right? All right, so let me give us another example under this guy. Most common example of E2, of elimination reaction. So imagine we have alkyl halide, we have CH3, CH2, let's say Br, and most of the time the base, this is stronger than NaOH. So this base is mostly used, and also potassium tertiary butoxide. So what is going to happen here is that once you see this is a strong base, so this is going to pull out HBr. This is the hydrohalogenation reaction. Now, class, this Br is going to come out from here. The H cannot still come out from this same guy. If the H is coming out from this same guy, that would have been 1, 1. Right? But we're not dealing with 1, 1, we're dealing with 1, 2. So if Br is coming out from this guy, right, the H has to come out from the carbon directly attached to this guy. It can be this, assuming we had another carbon here, it can either be this guy or the next one. But in the case of this next one, there are rules that we need to follow, right? So for this guy, we have, if I remove H from here, this becomes CH2. I have CH2 because if I remove Br from here, remains CH2, right? Plus the H that came out from here will now pick up the Br, and we have what? Now, there is a need for us to add a double bond because this carbon is shorting one bond each, right? So this becomes this. So this becomes ethene. This is bromo, one bromo, ethane, or ethyl bromide. So that's basically it. So let's look at another example of, so let's imagine we have something like this, CH3, CBr, now we have this. Now this is elimination reaction. So imagine you have something like this, right? And then you want to get the product. First thing first, it's very obvious that what is going to come out of this guy is, this is the hydrohalogenation reaction. HBr is going to be pulled out. Now, it's very obvious that we only have one Br. So Br is not a problem. But the issue right now is going to be the what? H, because we have lots of H here. Now, bear this at the back of your mind that the hydrogen that is going to come out would be the hydrogen on the adjacent carbon. That is, carbon directly attached to this. We have two of such carbon, this and this. Right? So between these two carbons here, which of them is the hydrogen going to come out from? Now, we're going to have two products. In any time you have listen, the carbon bearing the halogen is called the alpha carbon. It's called the what? That is why this stuff, most of the time, they also call it alpha beta elimination. Beta elimination is also called what? Alpha beta. That means the first guy is coming out from the alpha, the next guy is coming out from the what? So the carbon bearing the halogen is called the alpha carbon, right? The carbon directly attached to that alpha carbon is called the what? Beta. In the case of this guy, we had only one beta carbon. So that was why the product was just one product. Anytime you have just one beta carbon, the product is going to be how many? One. But anytime you have two different beta carbon, if I come here, and put this guy to be 3. These two beta carbons are the same. So it's still considered as being 1. Because this CH3, this is the same thing as this. So for those of us, these two carbons now, they are equivalent. So removing from here is equivalent to removing from here. So in as much as, yes, we have two beta carbons here, but these two beta carbons are equivalent. So therefore, they are seen as how many? 1. But if I come here and I say CH2, CH3, the two beta carbons here, they are not equivalent. This guy has 2 hydrogen. This guy has how many? So that means anytime we have two different beta carbons, we're going to have two products. We're going to have what? Two products. Now, depending on which rule they asked you, have you guys learned saytzeff rule in elimination? Saytzeff, Hofmann. Oh, now, please look up. So the product will be the H. If you remove one H from here, this becomes CH2, CH, CH2. Now, this is the first product. If the H comes out from here, the second product will be if the H comes out from this guy. This will now be CH3, CH, CH, CH3. Now, these are the two products, but one of them is going to be major, and the other one is going to be what? Depending on the rule that you're at. Depending on the what? But what if they do not mention any rule? We have default rule. We have what? Just like in Chem 132, Markov-Nikov, right? We have anti-Markov-Nikov, right? But in a case of where nothing is being mentioned, it's Markov-Nikov we are going to follow. So that's the same thing that is applicable here. Now, the big question is, if assuming you were asked for the major product, which of the hydrogen are you going to remove? This guy is correct. Is correct. Form the majority. So this guy, this guy has lesser number of hydrogen. Is it not so? So since the hydrogen is already going down, let's just finish it. That's the concept. So this is basically elimination reaction. So the concept of elimination reaction deals with removal of two molecules, right, from adjacent carbon to give, that's for 1, 2, to give us an alkene as a product. So having done this, there are mechanisms by which this guy is going to occur or take place. So that's what we are going to dive into now. We have the E1 mechanism, we have the E2 mechanism, and we have the E1. Where did they stop in this mechanism? Did they treat 3 of them? So we have elimination unimolecular. Most times I don't used to put this reaction. I just say elimination unimolecular. So you might decide not to put this reaction. It doesn't really matter. For me, I would even say don't put it. Because it's more like just when we said SN1, SN1 was substitution nucleophilic. I did not say substitution reaction nucleophilic. Do you understand? So I could even decide to remove it. So it's more like elimination unimolecular E1, elimination bimolecular E2. Please put down. In E2 elimination, the mechanism is a one-step process. The mechanism of E2 elimination is a one-step process. The mechanism of E2 is a one-step process. Full stop. In this mechanism, the carbon-hydrogen bond and the carbon-halogen bond is broken simultaneously. That is, in a concerted way. In this mechanism, the carbon-hydrogen bond and the carbon-halogen bond is broken simultaneously. Brackets, in a concerted way. Now, please continue. This means that as the base is pulling the hydrogen away from the carbon, this implies that, or this means that, as the base is pulling away the hydrogen from the carbon, comma, the halide is also simultaneously departing to form a double bond. The halide is also simultaneously departing to form a double bond. All right, so E2, please look up. Now we said the kinetics for E2 follows a second order kinetics. And this means that the rate of the reaction is dependent on both the substrate and the base. Which means if you increase the concentration, you increase the rate. That's basically what it means. If you increase the rate of the concentration of this guy, the reaction, the rate increases. If you increase the concentration of the base, it also increases. So either of these will actually affect the rate of the reaction. In case you're being asked, maybe they ask you to give the mechanism of a reaction, propose a mechanism, right? Just like what we did previously. Once you've done this, you do the reaction. This Rx, in place of the Rx, you just write out the substrate itself, right? The base, mostly, and they used to give us KOH and potassium tetrophthioxide, yeah? So we're going to look at that shortly. So let's see what else. It is called bimolecular because the rate of the reaction depends on both the concentration of the substrate and the base. Note, substrate with good leaving group and beta hydrogen. Note, substrate with a good leaving group and a beta hydrogen is normally used. Now, this is actually where these things now is what we try to understand the difference between E1 and E2. So that's point number one. A substrate with a good leaving group, because if the leaving group is poor, right? For example, OH is a very bad leaving group, so OH needs to be protonated before it can go out. So you cannot just pull it out like that, easy, right? So in this case now, for that OH to go out by itself, you need to do something. And if you do something, the step is no longer going to be one step. You have to take it to E1. E1 is a two-step that can accommodate three steps. Please take note that if the leaving group is poor, right, both for substitution and both for elimination, SN2 and E2 cannot go. But if it is SN1 can go, because if something is a poor leaving group, you can do something to that poor leaving group, right, for it to go out. And if you do that, you cannot, SN2 does not give room for that because it's a one-step process. But the one that has two-step process, you first of all form the carbocation, is it not so? Forming the carbocation will now give you a room. The process of forming that carbocation will give you a room to detach it by force. So take note that poor leaving group do not undergo SN2. They don't also undergo what? E2. But they can undergo what? SN1 or what? E1. And that's not just the only reason. I said also a beta hydrogen. Now, what is a beta hydrogen? A beta hydrogen is basically a hydrogen that is attached to a beta carbon. And what is a beta carbon? Carbon directly attached to the one bearing the halogen. So imagine if I have something like this. If I have this, this cannot undergo, this will not be able to undergo E2 because this is the alpha carbon here, right? This is a beta carbon. Is there any hydrogen on this guy? No, so there's no beta hydrogen here. So this guy cannot even attempt SN2 E2 at all, right? This is alpha and this is beta. There's no hydrogen here, so you cannot even attempt it. So take note of that as point number one. So let's finish the next point. Number two, E2 are generally run with a strong base. E2 are generally run with a strong base. They are generally run with a strong base. We have example of strong base. We have etc. Point number three, no rearrangement is encountered in E2, just like in SN2. No rearrangement is encountered in E2, just like the SN2. No rearrangement is encountered in E2, just like the SN2. Number four, Polar aprotic solvent favors E2. So let's look at E1 elimination. Mechanism of E1 reaction. E1 proceeds via a two-step mechanism. E1 proceeds via a two-step mechanism. The first step, breaking of let's assume we have something like this. Now, we say it's a two-step process, but I just want to explain the first step. The first step is breaking up the carbon-halogen bond to form a carbocation. So this is a carbon bearing the leaving group. So you break this guy. So this becomes, we have CH3 plus X minus. Now the second step will now be, this step is also called the ionization step. Take note of that. The first step is also called ionization step because you're breaking this guy to form the carbocation. So the second step is breaking of the carbon hydrogen bond now look at this. The first one is breaking of carbon halogen. The second guy is breaking of carbon hydrogen. So the hydrogen you're going to break out, listen, is always going to be the adjacent hydrogen, the one on the next carbon to this guy. You can't remove X from here and not remove H from here. If you remove X from here, the H has to come from the adjacent carbon. That's why it's a 1-2 elimination. So when you do that, this becomes CH2. I'll put this X here, this guy. Please look up. You can decide to put your base here. You can decide to put your base here. This guy pulls out this. Now, when he pulls out the hydrogen, here becomes, because this hydrogen is going to go out as H plus, here becomes minus. Minus plus forms a double bond. So we now have CH2, double bond, CH2 plus HP. Now, the second step is the fastest. So this is the first step is the rate determining step. That is why it's called E1. So it's just this first step that determines formation of the carbocation that determines how fast the reaction will go. So the slow step, that is energy demanding step. Which is also, the energy demanding step is also known as the rate determining step. That means it determines the rate of the reaction. Now this second guy is the fastest step. So that is that for E1. Some key points, notes. The first one is the kinetics. Please, E1 is a first order kinetics. E1 is a first order kinetics. Is a first order kinetics, and the rate law is equals to K. Now, The rate of this E1 is only dependent on the substrate because the first step is only involving the substrate. That's ionization step. This is a rate determining step. That is why there is no base involved. In the case of E2, both the base and the substrate were involved in the reaction process. But here, it's only the substrate that is involved in the rate determining step. So it's a first order kinetics. Number two, let's talk about the type of substrate that favors E1. Please pay attention. Pay attention. Now remember, since the first step of E1 is always formation of a carbocation, the more stable the carbocation would be, right, the more favored the reaction would be. I repeat, the first step of E1 reaction is formation of a carbocation, is it not so? And we all know that we have primary carbocation, secondary, and what? Tertiary. The more stable the carbocation would be, right, the more favored that particular substrate would be. So therefore, the best substrate for E1 is tertiary alkyl substrate because tertiary alkyl will give rise to tertiary carbocation, right? The best substrate is tertiary alkyl halide. So reactivity towards E1 is that tertiary is more reactive than primary, is secondary more reactive than primary. So the best substrate for that guy is tertiary. Another point you like to know. So that means from this guy, it's now very obvious that for E2, primary alkyl will be the best because that primary alkyl has more beta hydrogens, right? Now, let's look at this. This guy, let's look at tertiary. This is CH3, C. So in this case now, this tertiary carbocation is attached to 1, 2, and 3. Now here is secondary, attached to 1 and 2, and we have primary. Now if you noticed, if I have this guy, okay, same thing. In this case now, we are using the formation of a carbocation. If I remove this guy, the carbocation that we form here is tertiary. Tertiary is more stable than what? Secondary. And secondary is more stable than what? Primary. There's a particular pattern I wanted to use, but then maybe I'll just leave it when we start solving problems. Because it's going to make me to explain further. So let's look at the next key point. Yeah. All right, so let's look at this. Please put down. E1 are generally run with weaker bases. E1 are generally run with weaker bases. No, like another key point. I'm just trying to tell us these are things that will help us distinguish E1 from E2. Now, the first one is kinetics. The second guy is substrate. The third, remember in E2 we said they are run with strong bases. You should know so. And I'm telling us now that for E1 it is run with what? Weaker bases. But in this case now, the kinetics does not involve base. So the rate of this reaction is independent of the what? Base. So even if you use something that is very weak, the reaction is still going to do what? Proceed. Because the rate does not depend on the what? Base. So that's basically what it means. So we said E1 are generally run with weaker bases. Okay. Please put down. Note also, okay, number 4. Yeah. 3 was number 4. Number 4, branching at the beta carbons favors E1. Branching at the beta carbon favors E1. This is only used, or this is only adopted when E1 is competing with SN1. Let's not use only. This is majorly adopted. I said branching at the beta carbon favors E1, comma. This is majorly adopted when E1 is competing with SN1. Stop. Another point. Alcohols can also be used as a substrate for E1 mechanism. Alcohols can also be used as a substrate for E1 mechanism. alcohols can also be used as a substrate for E1 mechanism. Now let me show something. Let me show the mechanism using alcohol. Alcohol has a poor leaving group, which is a OH. So if you want to remove that guy, how do you go about it? So imagine they give us something like this. But before I proceed, the two most common substrates, the common substrates we are going to be seeing as follows: alkyl halide and alcohols. These are the two most common substrates you're going to be seeing. But you hardly see this guy has OH. And OH is a poor leaving group, right? So alcohols will never be used as a substrate for E2, right? It can only be used as a substrate for what? E1. Now look at this reaction. We have dehydration of alcohol to give alkene, chem 132 and chem 260. So you have this reaction here. We have CH2 plus water. Now, imagine you're asked to give the mechanism of this reaction. It's very obvious that acid, if this guy is a drying agent and also a dehydrating agent, so this guy is going to remove water from here. So which type of mechanism can we use? So just take note of that. This is exam question. So basically, how would they ask you? The examples I've shown us so far under elimination has always been that it's a base catalyzed. It's a what? So imagine now you're seeing an acid. How do you go about it? You don't have to panic. Now this is acid catalyzed dehydration of alcohol. This is elimination reaction. But you're seeing an acid instead of a what? A base. Now it's because OH is a poor what? Leaving group. Base, remember I told us that there is how a poor leaving group will be attached. Then you need to do something. So this is what we are going to do. I told us that E1 is how many steps? 2. But this guy is going to give us 3 steps. So for here, I'll say, since this is a substrate, we have CH3, CH2, OH. Class, OH is a poor leaving group. OH is a what? So since OH is a poor leaving group, I need to do something to this OH to convert it from a poor leaving group to a what? A good leaving group. So what I'm going to do here, I will say step 1, protonate the OH. That is the work of this H2SO4. Protonate this OH. So when I do that, this becomes CH3, CH2, this guy. So let's write it down so that I'll have space. CH3. Now, this is H2SO4. But this H2SO4 is going to split as H plus minus. So when you protonate, protonate simply means you're adding hydrogen to this guy. Please, the arrow is coming from this lone pair, not from the plus. Right? You protonate. You want to convert this guy from a poor leaving group to what? A good leaving group. So this becomes CH3, CH2. This is it. Now, this guy now, this water is now acting as a good leaving group now. As a what? So you can now kickstart the normal process of E1. What we just did here is not the normal process of E1, right? We only protonated. So we have succeeded in converting anytime you see a poor leaving group class, what you're simply going to do is to protonate. Is to do what? So if they give you a poor leaving group, they cannot give you a base catalyzed. A poor leaving group is always going to be what? Acid catalyzed. Are you following? Because once this guy is used to protonate this, what is remaining now is now a base. You get it now? Remember, if an acid loses proton, what is remaining is now a conjugate base, right? So the hydrogen in this acid is what is going to be used to convert this guy from a poor leaving group to a what? A good leaving group, right? This remaining guy will now act as a base to kickstart the E1 process. And what is the E1 process? Breaking of the carbon halogen bond. The carbon halogen bond was in a case where the leaving group was a halogen. Are you getting me? Class. We said carbon halogen bond because this guy was a halogen. This living group was halogen, right? But in this case now, is a living group halogen. So what we want to do now is that, remember, the first step was ionization step, right? We want to form a carbocation. And in forming a carbocation, the leaving group has to leave. In the case of this guy, this was the leaving group, right? In the case of this guy, this is meant to be the leaving group, but it's a poor leaving group. We've converted it from a poor leaving group to a what? A good leaving group. So I can now kickstart the process of E1. So I can just call this guy, let's just call it this. This is not really the initial, I'll just say the protonation step, like converting poor leaving group, to what? Good leaving group. So that's basically what this guy is all about. So this guy is now a good leaving group. So we can now kickstart our E1 process. Are you following? So this now becomes please, what was the first step of E1? Ionization, right? So this is now what we are going to use as a substrate now. So this becomes CH3, CH2. Let's take this guy up. Plus, is it not so? Right? So this is what we're going to do now. This guy breaks out. We now have CH3, CH2 what? Plus, and what? Water. It would have been very difficult for us to remove OH as a leaving group. But after protonating it, it now becomes water, right? So it's now very easy to remove what? Water. So this is now what we have. This is the first step. Now, please write so I can clean. It's a three-step process, yes. That's why it's a three-step process. You can decide to call this guy just protonation group. You can call it 1, 2, 3, doesn't matter. It's a three-step process. So this one is protonation. This one is what? Ionization. Now the third step is now going to be what? What was the third step? Breaking of the carbon hydrogen bond, right? By attack of the what? Base. Remember, right? So now, the hydrogen we are going to remove is no longer the hydrogen on this carbon. Right? It's going to be hydrogen on the adjacent carbon. Is it not so? So I come here, I'll say, I will no longer put CH3. I want to put the hydrogen down. So I'll write how many here? And then put one here. Is it not so? And then my carbocation. Then, class, the base we are going to use is now the HSO4 minus. Are you seeing it? Initially, they gave us as an acid, right? The H from this acid protonated this guy and formed water. This base, remember when they say acid catalyzed, at the end of the day, the acid is not meant to be used. So this H that was used has to be replaced back. So this becomes HSO4 minus. If I write it up, how will I now put the arrow? If you write it doesn't, if you write it up, that means the H has to do what? Go up. Or should we do it that way? Please, it doesn't matter if you can decide to put this guy up, but this H now has to go up so that you don't have to be crossing the line up and down. This now becomes CH2 double bond CH2. Can now say plus what? Now, the product of the reaction, this was what they gave us in the question. The question had CH2 double bond CH2 plus what? Water. This H2SO4 was the acid they started with, right? We did not use it. Remember, an acid, if a catalyst is something that at the end of the reaction, it will not be what? Consumed. elimination unimolecular conjugate base. It is a two-step process. The first step is breaking of the carbon hydrogen bond. Please remember, this is more like this is the opposite of E1. In E1, the first step was breaking of carbon halogen, and the second step was breaking of carbon hydrogen. In the case of E1CB, it is the opposite. So let's use this substrate. This is CH2X. Now here, the base pulls out this hydrogen and break this bond. I will now give a conjugate base. Remember, any substance, if an acid should lose a proton, what is remaining is going to be a conjugate base. So when this guy loses this hydrogen from here, you now have a minus. So that's why we call this guy E1CB. Right? Because what is going in the first one, what was formed first was a carbocation in E1, right? But in E1CB, what is formed is a minus. So the second step will now be breaking of carbon halogen bond. So this becomes look at this guy. There is an arrow here because this is a minus. So when this happens here, we have H2, H2 plus X minus. This is basically the product of this reaction. So this is basically E1CB. Breaking of carbon hydrogen first, which is actually done via the base. The base pulls out this guy to form a minus. Now the second step is breaking of carbon halogen bond. This X breaks out. The double bond here. This minus moves here to form a double bond. Yeah, it's on the C. But the C is okay like this. Please put down. Conditions necessary for E1CB. Number one, let's continue. And we said these are the conditions necessary for E1CB. Right? The condition is that, please take note of this condition. Most of the times, they will always ask you, if they want you to give something in E1CB, they always mention it. The few times I've seen E1CB question, they will always mention it. Yes, they will always mention it. They can just ask you to state the conditions necessary for E1CB. Number one is presence of electronegative atom or group on the beta carbon. Beta carbon is actually the carbon attached to the one bearing the halogen. Right? Now remember that electronegative atoms or group are those ones that withdraws or attract electrons, right? Negative I. To make beta hydrogen more acidic, example of such group is this, nitro, CN, and this. So anytime you see this guy attached to the beta carbon, all right, it's going to help the E1CB to proceed faster. Presence of a poor leaving group, right? A poor leaving group cannot go for E2, right? I just told us it can go for E1, right? Since this one is also E1CB, you can also use this method to remove that guy. Stabilization of the carbon ion. Remember, in the case of E1, the intermediate is always carbocation, is it not so? The more stable the carbocation is, the more favorable that reaction will be, is it not so? In this case now, we say stabilize anything that will stabilize the carbon ion. Carbon ion is carbon that has a negative charge, right? And that was the first product from E1CB. So stabilization of the carbon ion intermediate through electron withdrawal by an electronegative species through conjugation. That is, beta carbon should contain carbonyl group or any other stabilizing group. So let's say, for example, I have this is CH2X. Now this is a beta carbon. Imagine I have something like NO2. This NO2 here, if you break it down, NO2 is this. This is the structure of NO2. Because NO2 structure is this. This is how the structure looks like. So remember, in conjugated system, there is a double bond, a single bond, and a negative charge. Remember that if I have a double bond, this is a conjugated system. A double bond separated from a negative charge by what? Single bond. So if you attach NO2 or you attach carbonyl to this guy, because it said true electron withdrawing group, that is, beta carbon should contain this or any other stabilizing. If I come here, I put carbonyl. This is actually a resonance. Resonance will take place here. So this negative charge can come down here, and this guy do what? Come here. So these are the factors that would affect E1CB. So let's look at the rules. Now we said rules guiding elimination reaction. We have two basic rules. We have the saytzeff. We can either pronounce it saytzeff or anyhow you want to pronounce it, but that's the spelling. All right. Now we have the Hofmann rule. Now saytzeff is basically the conventional rule. And what does this saytzeff say? That it says that. So I said in saytzeff rule, this rule is basically used to determine which product to be major or minor. In a case where elimination reaction give rise to two products, right? Both of them is used to determine the stability, the one that will be more stable and the one that will be less stable. Each of them have their conditions. Number one condition is that, let's say, for example, I have something like this, CH3, CH, Br, CH2, CH3. Anytime you have two different types of beta carbons and beta hydrogens, right? That is basically when these two rules is going to be applied. You cannot apply this rule if you have substrate like this. If you have substrate like this, you cannot apply any of this rule because this guy has just one beta carbon. Now this is alpha, the carbon bearing the halogen. The carbon attached to the alpha is called the what? Beta. So anytime you have a compound that has just one beta carbon, these two rules will not be applied because the product is just going to be how many products? One. So in this case, I'm coming. This guy now will only give us one product because we only have one alpha carbon. If I come here and put CH3 here, this guy will also give us one product because these two are beta carbons are equivalent, right? Yes, we have two beta carbons, no doubt, but are two of them different? No, they are the same. So taking H from here is the same thing as taking what? H from here. So when we have something like this is the alpha carbon, this is beta, and this is beta. The carbon is directly attached to this guy, right? Now, the two beta carbons are not the same. They are not what? The same. In this case now, this rule comes into play. Now, it means that this compound, if you subject this guy to elimination reaction, you're going to have two products. One product would be by removing H from here and Br from here to form a double bond here. The other product would be removing H from here and Br from here to form a what? So between those two, now one of them will be the more stable and the other one will be the less stable. So that's basically what this stuff is telling us about. So let's look at what each of them is saying. So let's define saytzeff and afterwards define Hofmann. So let's say please sit down. During beta elimination reaction, saytzeff rule says that during beta elimination reaction, the major product or the most preferred product, is the alkene that has greater number of alkyl group attached to the double bonded carbons. It says that during beta elimination, the major product or the most preferred product is the alkene that has greater number of alkyl groups attached to the double bonded carbons. Now that is that for saytzeff. Now I just want to take the definitions, after which we're going to take some few examples. Now please put down. Hofmann rule states that during beta elimination, the major product is the alkene that has less number of alkyl groups attached to the double bonded carbons. Hofmann rule states that during beta elimination, the major product is the alkene that has lesser number of alkyl groups attached to the double bonded carbons. Note, for Hofmann, this normally happens when the attacking base is bulky. Now, this stuff is very simple. If you understood the first one, it's just the opposite of the first one. The first one says, if says during beta elimination, the more stable is the one that has greater number of alkyl substituents. Whereas in Hofmann, the major product is the one that have less number of alkyl substituents. Full stop. Now I said for Hofmann normally happens when the attacking base is bulky. When the attacking base is what? Bulky. Factors that favors Hofmann products. Factors that favors Hofmann products. Factors that favors Hofmann products. Number one, a very bulky base favors Hofmann products. A bulky base favors Hofmann products. Number two, if the leaving group is a charged molecule and also large. If the leaving group is a charged molecule and also large, such as something like this. So these are the two major factors. So let me tell us this. If you're comparing saytzeff with Hofmann, in a case if bulky base favors Hofmann, what do you think? Which type of base will favor saytzeff? Less bulky, right? Number two. Now, the substrate, the leaving group in Hofmann is always charged and large, right? Example is this. Whereas for saytzeff class, the leaving group that favors saytzeff is mostly halogens, bromine, iodine, chlorine, etc. Because for Hofmann, the leaving group has to be charged. That means it either has a positive charge or what? A negative charge. Not just that, it's going to be large, right? But in the case of saytzeff, the leaving group is always the normal halogens. Anytime you see halogens and then they did not make mention of Hofmann, right? You go with saytzeff. How would they ask a question based on that? Let me tell us. Majority of times, if they don't actually ask you Hofmann or saytzeff, they just say, give the major product in this elimination reaction, right? And then you look at the conditions. The base is not bulky. The substrate does not have a charged leaving group, right? What are you going to follow? Saytzeff. Now, let me give us an example. Imagine I have something like this. CH3, CH, Dr, CH3. Now, even without saying anything, this guy will favor saytzeff because the leaving group is a halogen, a small leaving group. But that does not mean that they cannot still ask you to give the Hofmann of this. You understand? They can still ask you to give the what? Hofmann. So now looking at this is the alpha carbon, the carbon bearing the halogen. This guy has beta carbon, beta 1 and what? The two beta carbons are not the same. So for the fact they are not the same, we have two different beta carbons here. Meaning that this guy is having CH3 and this guy is having what? They are not the same. It means that we are going to have how many products? Two. The first product will be removing Br and removing H from here. So when you do that, this becomes CH3, CH, double bond, CH, CH3. Plus, the second product will be removing Br and H from here. So this becomes CH2, double bond, CH, CH2, CH2. Now, according to saytzeff says the major product will be the one that has greater number of alkyl groups attached to the double bonded carbons, right? Now, the two carbons of the double bond is this guy. How many alkyl groups can you see is attached to this guy? One, one. One here, one here. That's total of how many alkyl groups? Two. This guy have two alkyl groups. Now look at this guy. How many alkyl groups can you see here? One, which is just this guy. So according to saytzeff, the most preferred or the major product to be the one that is more substituted, right? Between these two, which is more substituted? This guy. This guy has two alkyl substituents, and this guy has how many? One. So this is going to be the what? Major product, and this will be the what? Minor. This is according to saytzeff, right? According to saytzeff. But if I'm the one solving this, I don't have to give the product to know the one that is more stable. Just by looking at this, I can tell you the one that is more stable, because in exams they might just ask you for the major product. In exams, right, they may just say, give the major product of this. That means they are not interested in the minor. Do you understand? So if I'm asked, give the major product according to saytzeff, this is what I'm going to do, class. These are the two carbons that will lose the hydrogen. The major product according to saytzeff will be the double bond that will be formed when the hydrogen is removed from the carbon that has less number of hydrogens. We have these two beta carbon, beta 1 and beta what? 2. So according to saytzeff, since we want to form more stable alkyl group, if I remove hydrogen from here, I have shortened this alkyl group now. You understand? So according to saytzeff, without even giving the product, just looking at this reactant or substrate, I can tell the major. The major would be the alkene that will be formed when the hydrogen is pulled out from the beta carbon that has less number of what? Hydrogen, which is this guy. So if I remove H from here, I'll still have this CH3 here. I'm still going to have the what? But if I remove the H from here, I'm no longer going to have this CH3 here, right? So this is, according to saytzeff, this is a major product. But what if we were asked, according to Hofmann? According to Hofmann, based on this guy, according to Hofmann, Hofmann says the major product would be the one that is less substituted, right? So according to Hofmann, let's say according to Hofmann, using this same reaction, Hofmann, this will be the what? Major. Because this guy has how many substituents? This guy has how many? 1. And this guy has how many? Between 1 and 2, which of them is less? So according to Hofmann, this will be major. And this will be what? Minor. They are opposite of each other. Now, but there are some substrates that will be given to us. Like, imagine I come here, I remove this guy, and I put NH3 plus. Imagine I have this leaving group. This is bulky leaving group, and this is charged. So imagine you are asked to give the major product of this. We are still going to have these two guys. So this leaving group automatically has activated this guy for Hofmann. So even if they did not say according to Hofmann, they just say give the major product, right? The major product will be this guy, because this is the one that will give us the less number of substituents, right? But assuming they had given us this stuff now, and they said according to saytzeff, this would have been the answer. I want you to understand something. Number one, they can give you something that without extra comments, you use what you were told from your textbook. Your textbook says, or the concept here says, The condition that favors Hofmann is very bulky base. Example of those bulky base are those potassium tertiary butoxide I gave us earlier. That's a bulky base. Number two is a charged leaving group. Imagine they did not mention saytzeff, they did not mention Hofmann, and they gave us this guy, and they just say give the major product. I'll be like, what are the conditions that will actually aid me to get the answer? Is this leaving group halogen? No. Since they are not halogen, I will not go towards the saytzeff. Because saytzeff, the leaving group has to be halogen, right? And the rest of them. That's if I'm not told. But since I'm not told, this guy cannot go through the saytzeff because this is charged and this is bulky. So now, this is going to go through the what? Hofmann. So remove this guy. And if you remove this guy and one H from here, this is what you're going to have. If you remove this guy and one H from here, this is what you're going to have. So since this guy is bulky, I'm going to follow the what? Hofmann. And according to Hofmann, Hofmann says the more favored or the most stable product would be the one that is less substituted. This guy has just one alkyl substituent, and this guy has how many? So between 1 and 2, which of them is less substituted? So this will be the what? Final answer. Imagine you have compound like this. How many products do you think we are going to have? First thing first, for you to determine the number of products, this elimination reaction, right? Let's find out how many beta carbons that we have. This is alpha carbon, right? Carbon bearing the halogen. Now this is a beta. Beta 1, beta 2, and what? We have 3 beta carbons, but 2 of them, 2 are equivalent. Which one and which one? Beta 1 and beta 2, right? So since they're equivalent, I'll see them as what? 1. Meaning that if I take hydrogen from here, it will be the same thing as taking from here. So that means this compound is just having 2 types of beta carbons, right? Which is this and this, right? It means that we're going to have how many products? 2 products. So I'll come here, according to saytzeff, because this guy is a less bulky leaving group. So I'll have, if I remove Br and remove H from here, I have CH2, C, Br, double bond, sorry, and then we have CH3. So here we have Br and what? Removing H from here, plus coming back, remove Br from here and from here too. So we have CH3, CH2. Please be very careful. This stuff you're seeing here, in exams, they might switch this guy up. This stuff you're seeing can be written as, instead of putting the double bond down, we took out the double bond hydrogen from here and bromine. That's why we have double bond here, right? But they can decide to put this guy like this and then bring this one down. Basically, it's like us bringing this guy down and bringing this guy what? Up. So according to these 2 guys, now let's look up the 2 carbons of the double bond. According to saytzeff, how many alkyl group is attached to here? 1, 2, and what? This guy is how many? So according to saytzeff, the more stable will be the one that has more alkyl group, right? So which of these will be the major? The first. So that is that for elimination reaction class. With this now, what we have done now, you can actually smash your past question. I'm serious, for elimination reaction, you can smash it. What is remaining is now substitution.